Okay, in this video, we're going to go through some revision notes for Physics 0625 Cambridge IGCSE for topic 11, conduction, convection, and radiation, or methods of heat transfer in matter. So let's begin. To begin with, we have conduction. Conduction is the first method of energy transfer, which we're going to discuss, and this is the main method of energy transfer in solids. So solids can have energy transfer methods and by other methods. Energy can be transferred to them by other methods, but this is the main method of energy transfer, which is conduction. Conduction is a transfer of thermal energy from the hotter to the cooler object when two solids contact each other. This is best in metals due to its high number of free electrons. So conduction is technically transferring thermal energy or transferring heat from a hot object to a cold object. We all know the object with higher temperature has more heat and more thermal energy. So if we have a hot object and we have a cold object, transferring thermal energy from this hot object to this cold object when contacting both surfaces together is conduction. The reason this is the best in solids, especially metals, is because metals have a high number of free electrons, and electrons are a good conductor of heat and a good conductor of electricity. So they can carry both heat and electricity. Now, there are two mechanisms of conduction: atomic vibrations and free electron collisions. Metals use both. Metals perform conduction by both atomic vibrations and electrons conducting heat. But non-metals only transfer or perform conduction by atomic vibrations because there are no free electrons to move in non-metals. But anyways, we're going to study how conduction takes place in detail in non-metals and in metals. To begin with, let's start with non-metals. In non-metals, when the substance is heated, the particles at the very end, so let's take an example here. Let's take a pencil for an example. This is a pencil, okay? And suppose this pencil is this rod in the illustration. So when the substance is heated, the particles at this end are going to start to vibrate much more, and they're going to gain kinetic energy because when you heat a substance, it gains kinetic energy and they move faster. So this is the cool end and this is the hot end because we're adding heat here, okay? So the particles in this end are going to vibrate much more. As they start vibrating, the particles are going to start bumping into each other in collisions. So the particles here are going to bump into the particles here, and the particles here will bump into particles here, and here, and here, and here. These collisions will eventually transfer energy from atom to atom to atom until thermal equilibrium is achieved throughout the whole substance, until the heat energy flow that was applied here is passed on to the whole substance to the cooler end from atom to atom to atom due to the number of collisions due to the high amount of kinetic energy we applied here. So again, in non-metals, the hot object, this is a glass rod where we're adding heat. This part, this is the cold part, this is the hot part. As you can see, the atoms are vibrating much more and they're just transferring kinetic energy by bumping into each other to the cold end. In metals, it is the same. So suppose this is a metal, okay? Energy is flowing here by the same method as atomic vibrations, but we have free electrons randomized in between the particles. These free electrons allow the energy or heat to be moved much faster than non-metals because electrons are a good conductor of heat. This is a relative thermal conductivity graph. So the best conductors are the worst. Sorry, the best conductors and best insulators. So the best conductors are the worst insulators, and the best insulators are the worst conductors because conduct means to conduct, to take in. Insulate means to prevent it from being taken inside, okay? So the best conductors are diamond, silver, copper, aluminum, steel, lead. The worst conductors, which are the best insulators, are glass, wool, rubber, wood, and ice, marble, glass. These are somewhere in between. They're not really good conductors, nor are they really bad insulators. Conduction, that was conduction in solids. Conduction in fluids, there isn't really much conduction in fluids because, like I said, it's the main method of conduction in solids. But It can happen in fluids like liquids and gases, but the problem is they are very poor conductors of heat because the particles aren't close enough for vibrations. Because when we're heating, the particles need to vibrate from one to another, from one to another, and bump into each other from atom to atom to atom to atom to transfer heat and reach thermal equilibrium throughout the whole material. But the problem in fluids is that the particles are very far from each other when compared to the solid. This is why the vibrations is going to be very difficult for them to pass along each other, and this is why they are very poor conductors of heat, and conduction does not relatively take place in the fluids. Factors affecting rate of conduction: the thickness of an object, directly proportional. If an object is more thick, the rate of conduction is going to be faster. Length is inversely proportional. If the object is smaller in length, okay, it will be easier because there will be less number of particles. So it will be easier to transfer the kinetic energy and heat from this end to the other end. The type of material, of course, like for example, copper and magnesium, heating both at one end to the other, depends on the type of material and its infrastructure, will determine how fast it transfers energy from one end to energy, depending on how well its infrastructure conducts heat. Difference in temperature at both ends. Investigating conduction. So it's a very, very simple experiment with only 3 steps to investigate conduction, where we get 2 rods of the same length. So we have 2 rods of approximately, of course, this is not same length here, but 2 rods of the same length, okay, congruent, okay, and we expose both rods, okay, to the same heater, okay, and then we put some sort of wax at the end of both rods. Make sure to put the same amount of wax, and then we just wait and measure which rod, from which rod does the wax burn away faster. This way we can determine which material conducts or is a better conductor. And that's all about conduction. Now let's move to convection. Convection is the main method of energy transfer in fluids, liquids, and gases. Like conduction was for solids, but it didn't apply so well in fluids. This one is mainly for fluids and does not apply so well to solids. So this one transfers thermal energy through a material by movement of the material itself. In conduction, the material is still, nothing is happening to the material, okay? But we're applying heat and the particles are moving atom to atom to atom to transfer energy. Convection, we're going to make the material itself move to transfer energy. This one only occurs in fluids and does not occur in solids. To understand convection, convection works by the convection current. What is a convection current? It's a simple movement of fluids that carries energy from a warmer to a cooler place. So, conduction is transferring energy from a hot to a cool place by contacting the solids together. Convection current does the same job of conduction, but by moving the fluid itself. Because the fluid is going to carry energy from a hot place to a cold place. How it works is very simple. So we have a fluid. When this fluid is heated, it will begin to expand, okay? We have fluid. The fluid, we're going to add heat energy to it, and the fluid will begin to expand. During expansion, what does expansion really mean? Expansion is increasing the volume, right? As we studied in the previous chapter, thermal expansion is increasing the volume of a substance. So increasing the volume and decreasing its density, because volume is inversely proportional to an object's density. So expansion will increase the volume of a substance, decrease its density, and keep the mass the same. Now, since this material is less dense than its surroundings, it's a fluid, it's less than the surroundings, it's going to float upwards and be replaced by the colder one above it with high density that will sink down. So again, for example, let's take air for example. Air is a very good example. Air is a fluid. Air is a gas, which is a fluid. As we heat air, the air is going to expand. This will increase the volume, decrease the density, and mass is the same. But it will expand. Since the density of this object, this air is going to decrease, now we know less dense things float up and heavy dense things come down. Because the air is going to expand, density will decrease is going to begin to float up because the density is decreasing. And whatever was up is now more dense than the air that's going up. So since it's more dense, it's going to sink down. So the heated air, heated air that we heated, and now that it expanded and decreases density and it's floated up, is just going to go up. And the cooler air with a much higher density is going to come down. And the cycle keeps repeating. This is the convection current. Now we're going to take some examples of the convection current to really understand it well. Heater on the floor. Heater on the floor, when heated, it pushes the molecules other apart, making the fluid expand. So like I said, you heat the fluid expands. This makes the hot fluid less dense in the surroundings. Yes, if you expand the fluid, it will become less dense in the surroundings and hence rising up, and cooler one comes down. And eventually this will repeat the cycle and create a convection current. An AC unit up on the wall. So I'm pretty sure we all have AC units, or we've all seen an AC unit and how it works. So what's actually happening in an AC unit? How does convection current work in the AC unit? In the AC unit, when the fluid is cooled, the molecules begin to move together and they make the fluid contract because the molecules coming together and they're making the fluid contract. This makes the hot fluid actually less dense than the surroundings, and it's going to rise up, making the cooler one come down. Eventually, the hot fluid will also contract over a period of time, sink back down, and it will just create a convection current because it's going to go back up, causing the cooler one to come back down, and it will keep repeating the cycle. For the third example, we have a fridge or a refrigerator. For this one, the freezing surface, if you've noticed on all fridges, is always on the top and on the back because the cold air sinks to the bottom and the warm air rises to replace the cold air as it's sinking. So warm air is always replaced by the cool air. This is why they're always in the top and in the back. Those are the three major examples. Another example is the motion of ocean water. With that, we have covered convection and conduction. Convection, main method of heat energy transfer in fluids, while conduction is the main method of heat energy transfer in solids. The third method of heat energy transfer is infrared radiation, IR. This is an electromagnetic radiation, EM radiation, with a wavelength greater than that of visible light. That's the definition of infrared radiation. Some very important facts to remember about infrared radiation. All objects give off radiation. Every single object that can be said as matter, or every single object determined as a matter, gives off infrared radiation. Infrared radiation is invisible to the naked eye as it is an electromagnetic EM wave, and it's the only form of thermal energy transfer. Only form of thermal energy transfer that does not involve the movement of particles, and it can travel through a vacuum. Vacuum means empty space, and infrared can travel through empty space, vacuum. That's number one. Number two, it does not involve movement of particles. It just travels as waves. There is no movement of particles. Of course, waves does have photons, but it doesn't involve movement of particles to transfer energy. It's part of the electromagnetic spectrum or EM radiation. It warms the object that absorbs it. Of course, since it's a type of radiation, any object that absorbs infrared radiation is going to warm up, and the more the object absorbs, the more it emits infrared radiation. It can be detected by nerve cells in the skin, though we cannot see it by the naked eye. The color of an object really affects how good it is at emitting and absorbing thermal radiation, and we're going to study that in the factors affecting thermal radiation. Thermal equilibrium. Let's look at this example. As an object is absorbing thermal radiation, it's becoming hotter, right? So we have an object heating it up, and as we're heating it up, it's absorbing thermal radiation, it's becoming hotter. As it gets hotter, it also emits more radiation. Like we said, the more object absorbs IR, the more it emits IR. Eventually, it will reach a point of constant temperature where the absorbing rate of radiation will become the same as the emitting rate of radiation. And if this rate at which the object receives energy now is less than that of which it transfers, it cools down because it receives some, but it's less than the way it transfers. It's transferring more energy out. So you're getting heat, but you're giving out more heat. So you're losing more heat, so you're cooling down. If it takes in more heat and gives out less heat, it's heating up. Because you're not giving as much as heat out, but you're absorbing a lot of heat, so you're heating up. And this point, the point in between heating up and cooling down, where absorbing rate is at equilibrium with emission rate, is known as the thermal equilibrium. And this is an example for thermal equilibrium where the emission rate, which is in no, the emission rate in yellow is directly equal to the absorption rate. Factors affecting radiation: surface area, directly proportional. The more the surface area of an object, the more radiation or rate of radiation. Distance is inversely proportional. Of course, for example, the sun and the earth. The sun giving radiation to the earth. If there was less distance between the sun and the earth, we would be receiving more radiation because it would take less time for the radiation waves to reach from the sun to the earth. Surface color, very important. Texture of the surface and difference in temperature. By texture, we mean smooth or shiny. Or shiny and dull. Okay, so now we're gonna understand why surface color is very important. Because surface color plays a vital role in absorbers, emitters, and reflectors in radiation. Good absorbers and emitters. We said all objects absorb IR and emit IR, right? Any good absorber and good emitter is a bad reflector. And any good reflector of heat are bad absorbers and emitters. So thumb rule, good absorber and emitter is bad reflector. Good reflector is bad absorber and emitter. The best reflectors, which are the worst absorbers and emitters, are shiny and white surfaces. And the best absorbers and emitters, which are the worst reflectors, are matte black surfaces. Not black, but matte black. Black absorbs well, it's a good absorber and good emitter. Dull and dark is a reasonable absorber, reasonable emitter, not as much. White is very poor. This is why on a hot day, you're going to see that you're going to, if you're wearing black, you're going to absorb much more heat, much more heat than somebody who's wearing white, because white is a poor absorber. Shinies are very poor absorbers and very poor emitters. Now, how do we investigate thermal radiation? So we have 4 steps in this experiment. First, we have to set up 4 identical flasks painted black, gray, silver, and white. So if you look at the diagram, we have 4 identical flasks. One is painted black, one is painted gray, one is painted silver, one is painted white. Now fill all of them with the same amount of hot water at the same temperature. Dependent variable, hot water, same amount. Temperature, same amount. And record their initial temperature and drop in temperature at regular intervals over a long period of time. The temperature in the black container will drop much more than white and light containers. So we have 4 flasks of equal flasks, similar flasks, equal water and temperature should be applied, and we investigate the rate of temperature in the 4 colors. The equipment we're going to need to perform this experiment successfully is we need a kettle to boil the water, to heat it up, to put the water inside the flask. We need 4 thermometers, 1 for each flask. We need flasks, of course, painted with different colors to investigate the amount of heat lost from each color. We need a heat-proof mat to prevent the surface and to prevent any heat lost from the flask. We need a stopwatch, of course, to record the time to cool. So analysis of our results. Most of the heat from the lost beakers is going to be through conduction and convection. And to compare the rate of heat loss, we can plot a graph with temperature on the y-axis and time on the x-axis. So this is a graph, temperature and time, showing the rate of radiation and heat loss of silver, white, dull, and black flasks. Black cooled the fastest, dull was second fastest, white was second slowest, and silver was the slowest. You can even plot a table like this. Usually in the exam, plotting a table is optional, but it will help you to make a good analysis for your graph. Now, evaluating this experiment, we should use a data logger for accurate readings, and our thermometer when performing this experiment should not be too big, otherwise heat will escape through the hole. And we should take repeated readings for each color flask to avoid one error. And we should read the thermometer values at eye level perpendicular to avoid parallax error and not to overfill the flask. Keep the volume of all flasks the same. Our variables in this experiment, the independent variable is color. This is the one that we're changing in the experiment because we're experimenting this at different colors. Our dependent variable is temperature because we're going to be measuring the temperature. And control variables are the identical flask, same amount of hot water, same temperature, and same time interval. These are the variables that must remain constant throughout the whole experiment. That's all for investigating thermal radiation, and our last part for this chapter is insulation and home insulation. Home insulation is usually used to prevent our house from getting very hot during warm weather. This is an example of a house, and some insulation is applied in this house, but we're actually going to study this in more detail with this table. So these are some quick and easy methods. Thick curtains, they stop convection currents and prevent thermal energy transfer. Underfloor insulating materials, they prevent conduction of thermal energy through the walls and the floors. Cavity walls are walls that are either double or triple layered. We have the wall, then we have some cavity put in between, then we have the other side of the wall. Or triple layered, wall, then cavity, then wall, then another cavity, then wall. This reduces thermal energy loss or gain by conduction. It's usually used in very luxurious houses. Foam or rock wool in the wall cavity. This one further reduces thermal energy. So we have the cavity wall, cavity, wall. And then in between both sides of the cavity, we have rock wool or foam in the cavity to further reduce thermal energy. This is especially used in very cold places like, very hot places like America or Texas. And the opposite is used in cold places like Antarctica and stuff. This is an example of a cavity wall. The first one is just a normal cavity wall. It reduces the thermal energy loss by conduction because air is a good insulator. But the second one, when you fill it with a cavity of foam or rock or wool, this prevents convection currents from forming. So the normal one prevents conduction, but the second one prevents convection currents. Vacuum flasks. So vacuum flask is a specific type of flasks that either keeps hot drinks hot or cold drinks cold. So it keeps anything hot, it keeps it hot, or anything cold, it keeps it cold. Okay? The structure of a vacuum flask is all you need to know for the vacuum flask. You need to know three things. It has glass, which acts as an insulator. It has silver coating on the glass, so the glass is already insulating, but silver coating on the glass reduces losses by radiation by reflecting away any IR radiation. And as you can see, it has a vacuum in between here, This allows air to be removed from the gap between the double walls to reduce the loss by conduction and convection, since it needs a material to travel through it. Okay, thermometers. So we finished everything about insulation. Now, thermometers, we're going to study two types of thermometers, a liquid glass thermometer and a thermocouple. The liquid glass thermometer, this is the structure of the liquid glass thermometer. It's like a rod-shaped thermometer with a wide circle opening here. Outside, you'll find the bulb. Inside, there's mercury heat-sensitive liquid. It uses expansion of mercury, and there's a tube to measure the readings here. When the temperature of mercury increases, its volume increases and it rises in the tube. This is thermal expansion. It can be calibrated by putting it in the melting ice to record 0 Celsius and record 100 degrees Celsius. So we have the thermometer, record it for 0 and record it for 100 because these are the two fixed points on a thermometer. Now use ratio to find the other readings in the thermometer. Simple as that. Thermocouple, on the other hand, this is the diagram or structure. It's shaped like this. It has a voltmeter in the middle. It has one metal inside, which is metal Y, metal X on the outside, two outside metal X, and hot junction on the left side, cold junction on the right side. When the junction is heated on either sides, it creates a potential difference in voltmeter. We're going to study what potential difference is in the electricity chapter. And its voltage can be compared to the temperature of the hot junction. This is how we can measure the alterations in temperature of a thermocouple. So to summarize this huge chapter, we're going to use the Save My Exam summary to give a quick review of everything we've taken from the beginning, or let's say the key points that we need to remember from this chapter. Conduction. Conduction, when atoms are heated, again, it only occurs in solids. Atoms are heated, they vibrate more, transferring kinetic energy from one to another. Metals are excellent conductors because they have free electrons. When metals are poor, gases are very poor. And for example, this is a mug. Mug becomes hot and heat is transferred from the cold hands to warm them up. This is conduction. Convection is transfer of heat energy in liquids and gases, mainly fluids. Does not occur in solids because particles are far away and they're able to flow past each other. Conduction is by direct contact between solids. Convection is when the material itself is moving. And this is an example of thermal radiation, where radiation is being emitted outside. So radiation is being absorbed by the cup and it's being emitted outside. The more it absorbs, the more it emits. Objects will always lose heat until they reach the thermal equilibrium. What is thermal equilibrium? Thermal equilibrium is where your absorbing rate of IR is equal to your emission rate of IR. When your emission rate and absorbing rate is equal to the surroundings, you have reached thermal equilibrium. For example, a mug of hot tea will always cool down until it reaches the room temperature, because once it reaches the room temperature, all the temperature of its emission and absorption is going to be the same, and at this point it will be in thermal equilibrium.